Welcome to my video tutorial for my personal project. I've been investigating running blades and have prepared this video to detail one of my dynamic models. Here I am modelling a severe loading scenario for one of the blade designs. From the assembly we can see the blade is marginally offset from the contact surface by roughly 5 mm. Moving into the load module, we can take a look at some of the loads and boundary conditions applied to the blade. In the module tree, we can see gravity has been applied. This accounted for the mass of the blade. This was input as minus 9,810 with the units of millimeters per second in the Y direction. Secondly, a user load was input. This accounted for a 700 Newton load of the user spread across the upper blade contact surface. Moving into the boundary conditions, we had a fixed floor, which ensured the contact surface remained fixed in place, despite any contact from the blade. And secondly, we had a blade guide. Input as 1200 millimeters, this guided the upper section of the blade through its contact and ensured no backwards falling occurred. This was given the amplitude blade guide, which ensured the model knew how far along the upper of the blade should be with respect to each time step. Now let's look at some of the results. Here we can see the contact of the blade. If we bring the model back to the start, we can play and have a look as the model progresses. In this model, all blue regions correlate to regions of low stress, whereas red or amber regions have high stress. In each frame, we can move it singly to identify where stress is high in the blade and at what point. Here we can see the maximum stress equated to roughly 3.5 von Mises times 10 to the 2. We can then see the blade continues and exits the foot strike. This was a severe loading scenario where the vertical force was increased above average to ensure the blade held up to any safety or performance standards required.